So let's start today's class. Okay. So before discussing the thing for today, let me briefly discuss things that has been done in the previous class. Okay. The previous class we have started the discussion from the entropic principle. So entropic principle states that delta is U, that is change in entropy in the system plus the change in entropy in the surroundings associated with any process, any naturally occurring processes should be greater than equal to 0. So this is the called the entropic principle. Okay, so for any naturally occurring processes, so that means the processes that is happening in the system. So it both includes the change in entropy in the system as well also the change in entropy in the surroundings. The total change, that is a change in entropy in the universe, should be always greater than 0. Uh, Next, we discuss the change in entropy for some processes. Okay, so first process we have discussed about the free expansion of the gas. For the free expansion, change in free expansion means what? Free expansion means uh, the temperature remains unchanged, okay, during the expansion of gas. So delta U basically equal to 0. This is the property of free expansion. And for this case, the change in entropy, that is delta S T, will be equal to NR ln V2 by V1. Okay. This is the change in entropy for the case of free expansion. Next, we have discussed a general expression of change in entropy for any kind of processes. So that general formula basically comes from the first law of thermodynamics, that is dq equal to du plus dw. You can write this as TdS equal to CvdT and CvdT plus Ed. Now you can write this, if you do the integration, you can write change in entropy for a general system. So that formula is given by delta S equal to NCV ln T2 by T1 plus NR ln V2 by V1. Okay, so this is the entropy change for general process, for any general process. Yeah. Next, we have also discussed the change in entropy due to diffusion, right? So like if like there are two types of gas, 1 and 2. So initially, each of them has a similar temperature and pressure. Now, if you mix them, if you mix the two gases, 1 plus 2, let's suppose type 1 gas has N1 mole and type 2 gas has N2 moles. Now, when you mix them, N1 plus N1, when you basically remove this divider, so those two gases basically diffuse, and due to diffusion, they like mixes two types of gas, and because of that, the change in entropy because of this diffusion process is basically given by delta S equal to general form summation I Ni R ln summation of I Ni by N by N. Now for this case, since there are two components gas is there, so in this case it will be delta S would be N1 R ln N1 plus N2 by N1 plus N2 R ln N1 plus N2 by N2. Okay. This is for this case. So this is the general formula. So this is the entropy for diffusion. Okay. Entropy for diffusion. Next we have discussed about different types of processes in a TS diagram. So previously we know about the PV diagram. Now if you want to convert the PV diagram into a TS diagram, so in that case you have to basically do a coordinate transformation. So we have done that, right? So in PV diagram, how the things looks like basically. Isochoric process looks like this, where volume is constant. This is isochoric. Isobaric process looks like this, where pressure remains constant. And isothermal process looks like this. This is isothermal. And an adiabatic process looks like this. Which has a steeper slope compared to the isothermal process. This is adiabatic. Now, if you convert them into TS diagram by calculating the slope in terms of temperature and entropy TNS, so in that case, these curves will take a different shape. Okay, for different types of processes. So TS. So the adiabatic process in this case, the adiabatic process have slope basically infinite. Okay, so adiabatic process looks like this. Isothermal process has a slope 0, so it looks like this with constant temperature. This is adiabatic, and this is isothermal. The isobaric process looks like this, and isochoric process looks like this. It's the isobar, and this is isochoric. Okay. This thing I have discussed, like okay.
Isochoric has higher slope than isobaric, right?
Yes. Isochoric has higher slope. The reason is because of the basically the value of Cp is higher than Cv. Okay.
Okay.
Cp, the slope is basically related to uh, inverse of their like heat capacity. So for isochoric process, dT by ds at constant volume is equal to 1 by Cv, T by Cv, and for isobaric it is dT by ds at constant pressure T by Cp. Okay. So since Cp is higher than Cv, so the slope in dT by ds at constant pressure would be lower than dT by ds at constant volume. Okay. So this is the reason why isochoric process has a higher slope compared to isobaric. Okay. Next we discuss about the TS diagram. Okay, so uh, if your TS diagram looks like this, if this is, let's suppose the temperature, higher temperature T2, this is the lower temperature T1, this is the lower entropy S1, this is higher entropy S2. So this is, let's suppose a cyclic process is happening in this TS diagrams. In that case, we have discussed the curve that corresponding to the high temperature T2. So the region bounded by that curve gives you the heat input into the system. Basically, this region. And the region that is bounded inside the curve, that gives you the total work done. Okay. This is heat input. This is the work done. Now, if you calculate these two things, you can calculate by using simple geometry also, or also you can calculate these things by using the formulas. Okay. So either way you can calculate. So the main thing is, by calculating these two quantity, you can actually get the efficiency of the cyclic process. Okay. So eta we know is basically work done by Q heat input, right? So by calculating these two things, you can get what is the efficiency of this cycle of heat. Next, we have discussed about two types of cycle, right? Heat engine, you can say. One is the Otto cycle. So for the Otto cycle, the PV diagram looks like this. We have discussed. And for this case, the efficiency of this cycle is basically given by eta equal to 1 by 1 minus R gamma minus 1. This R is basically the compression ratio. This R equal to V1 by V2. And next we have discussed about the diesel cycle, right? So for the case of diesel cycle, the PV diagram looks like this. Here the efficiency given by this formula, is equal to 1 minus R gamma minus 1 into rho gamma minus 1 into gamma by rho gamma into rho minus 1. Here R is the compression ratio V1 by V2, and rho is the fuel cutoff ratio. That is, rho is V3 by V2. Okay. So the difference between this Otto cycle and diesel cycle, as you can see from the PV diagram also, this part, this is basically this curve is coming because of the combustion process, I guess. This is because of, yeah, this is the combustion process. Okay, so in case of Otto cycle, this combustion process is basically an isobaric process. So this is isobaric. And for the diesel cycle, this combustion process is isochoric. Okay. These are the two main difference between the Otto cycle and diesel cycle. Okay. Yeah. So these are the pretty much things that we have discussed in the last class. Now for today's class, we'll start something new. So in today's class, we mostly discuss about different types of Maxwell relations and thermodynamic potentials and their relations, and what are the formulas that are necessary to solve the problems. Okay. Yeah. So let's start from the Maxwell relations. Okay. as you know, there is a process to remember this. This there is a mnemonic basically. So using that, you remember this Maxwell relation for thermodynamics. So that is given by this diagram S P T E. Okay. So now in this diagram, we have to go into the clockwise direction. Okay, like this. So the thing is first between S to P. Okay, so S and P. So how S and P are related? So del S, del V. So S with respect to derivative with respect to V, and equal to del P with respect to P derivative with respect to T. Okay. And in this process, for S, for the case of del S del V, the temperature is constant, and for del P del T, the volume is constant. Okay. Similarly, so we have done this first relation. Next, for P and T. For P and T, what would be the derivative? Del P by del S, del P by del S equal to del T by del V. Okay. So it moving like this. So del P by del S into equal to del T by del V. Okay. And when you move from like this horizontal line to the vertical line from like S to P to P to T, in that case there is a minus sign involved. Okay, so there will be a minus sign. And for this case also del P del S, the volume is constant, and in this case entropy is constant. Similarly, the other two relations would be del T del P at constant S will be equal to del B del S at constant T, and the fourth relation is del S del P at constant T minus del V del T at constant T. Okay, so these are the four relations. Okay, Maxwell relations. So these are very important relations. So to solve any kind of algebraical problem in that is regarding to this thermodynamic potential, okay, some quantity we may have to prove, okay, the right hand side, left hand side. So in order to prove that, you have to basically substitute this relations in between the steps actually to basically get the desired quantity. Okay. So in that way, these relations to remember these relations are quite important. Okay. Uh, yeah. Also, you can write these relations in different way. Also, like this relation, like uh, del S del P at constant T equal to minus del V del T at constant T. You can multiply T both the sides. Okay. So it will become T del S del P equal to minus T del V del T. Now TDS, you know, dq equal to TDS. Okay, so you can write this thing as dq by dp at constant equal to, and you know this volume expansibility, that is alpha. Alpha is basically 1 by v del T, right? At constant pressure. So you can write this thing as minus T V into alpha. This is a also important relation you can prove from a Maxwell relation. Okay. There are other things also, like from del S del V at constant T equal to del P del T at constant T. From here also, if you multiply T both sides, you will get del Q del V at constant T equal to T into del P del T at constant T. Okay. Now we'll discuss. So these are the some basic like implications of this Maxwell relations. The first thing is you have to remember all these four relations. Actually, this is quite important. Next are the TDS equations. Okay. Yeah. So TDS equations are also very important equation basically in the field of thermodynamics, because it basically relates what is the change in entropy, like ds, with the other thermodynamic quantities like dp, dv that actually can be measurable. Okay? So in this perspective, this TDS equations plays a very important role. So first thing is, you can remember this TDS equation, or you can take 10 seconds to derive it. Okay. So for any kind of problem. Okay. So TDS equation. So TDS equations. So the first TDS equation, what you can do, there are three thermodynamic coordinates are there, E, V, and T. Okay. And entropy. So we can take any of these two coordinate as an independent coordinate. Okay. To basically express the entropy. Okay. So for the first TDS equation, what we generally do, the entropy as a function of T and V. We will take T and V as a independent coordinate, and we write the entropy in terms of T and V. So the total derivative of entropy ds, you can write it as del S del T at constant V into dt plus del S del V at constant T into dV. Okay. Now, since it's called as TDS equation, so we multiply T both the sides. TDS equal to T into del S del T at constant volume dt plus T into del S del V at constant to dV. Okay. Now, yeah. So now from here, you know that dq is basically cv dt. For in the case of volume constant, if volume is constant, so that means TDS is basically CVDT. So we can substitute this thing here. After doing that, TDS will become CVDT plus T into, and this del S del V, we can use this what is this one? Del S del V. Yeah, this first Maxwell relation, del S del V equal to del P by del T. So we'll substitute it here. So T into del P del T at constant volume T. First one is constant temperature, now it become constant volume. Okay. So this is one way of writing the first TDS equation. You can further simplify this equation. So in order to do it, you can write del P del T as minus del P by del V at constant temperature into del V del T at constant pressure. Okay. So if you substitute here, in that case you can write this TDS equation as Cv dt minus T del P del V at constant temperature and del V del T at constant pressure. Now you can write this thing in terms of volume expansibility and compressibility of the gas. So that we know that their expressions, corresponding expression we know, alpha is basically 1 by V del T, and this Et is minus V del P del V, right? So now if you substitute these two things here, then you can write this expression as plus T alpha Et into dV. Okay. Okay, so this is this equation 1 and 2, both are known as the first TDS equation. Okay. So you can either remember just its form of the equation, or what you can also do, you can take like it will at least take like at most take 10 to 15 seconds to derive it. Okay, so you can derive it also. It's better to remember. Okay, by doing the derivation. Okay. The second equation is the second TDS equation. So in that case, for the second TDS equation, so for the first we have taken T and V as an independent coordinate. For second TDS equation, the temperature and pressure would be the independent coordinates. So S would be function of temperature and pressure. Okay. Similar way, we can write ds as del S del T at constant P dt plus del S del P at T into constant of into dP, constant temperature into dP. A similar way, if you do, we'll get TDS equal to Cp into dt minus T del V del T at constant pressure dP. Or just like the first TDS equation, this also you can write it in terms of volume expansibility. Okay, so TDS will be equal to Cp dt minus T into V alpha dP. Okay. So 1, 2, this will be 3, 4. So these 3, 4 are basically the second TDS equation. Okay. And third one, as we have guessed already, so for the third case, the pressure and volume would be fixed. So for the third TDS equation, the entropy would be so the independent coordinates would be pressure and volume. So we can write similarly ds, the total derivative ds as del S del P at constant volume dP plus del S del V at constant pressure dV. Similarly, if you simplified it further, we'll get TDS equal to Cp del T del V at constant pressure into dV plus Cv del T del P at constant volume dP. So this is the third TDS equation. Okay, third TDS equation. So first, second, and third. So so to do the derivation, you have to just remember for the first case, for the first TDS equation, it should be the function of temperature and volume. For second case, it should be temperature and pressure, and for a third case, it should be pressure and volume. Okay. And after doing that, just take the total derivative and try to write the things in terms of the specific heat like Cp, Cv, and by doing that, you will get the form of the TDS equation. Okay. Okay. So these are the two TDS equations. So next is the energy equation. Okay. So this is also a very important point. So TDS equation, what it gives us? It gives us basically from for a thermodynamic system, what the things you can basically calculate are related to pressure, temperature, and volume, right? So how this pressure, temperature, and volume basically related to change in the entropy of the system. That relations basically governed by these three types of TDS equation. As you can see, all these three TDS equation give some relation of the entropy with the variables like temperature change, Cv, that is related with the volume, or pressure, Cp. Okay, these are basically the measurable quantities of a thermodynamic system. Okay, so by using these relations, you can basically get a bridge between this standard thermodynamic variables with the along with the change in entropy. Okay. Next is the energy equation. Okay, so energy equation is the reason of this energy equation exist is that Similar way, okay. So how this change in variable like pressure, volume, and temperature related with the change in the total energy of the system or the internal energy of the system. So using this energy equation, you can basically measure the change in the internal energy of the system. Okay, so it can be derived from the first law of thermodynamics, that is dq equal to du plus dw. So you can write it like this: d equal to dq minus dw. So du equal to dq can write as tds and dw can write as pdv. Uh, Now using the first TDS equations, first TDS equation you already know. This basically this equation. If you substitute this TDS here using first TDS equation, substitute it here, you will get d equal to Cv dt plus T into del P into V minus P dV. Okay. Now, so this is so now also now now U is also variable of the U will also function of temperature and volume. Okay, so to write the total derivative of U, d equal to del U del T at constant volume dt plus del U del V at constant temperature dV. Okay. So now if you compare this equation 3 and equation 4, in that case you will get del U del T at constant volume will be equal to Cv. Okay. So this is one relation that we get. This relation, anyway, you already knew this relation. The next relation that you will get as del U del V at constant temperature will be equal to T into del P del T at constant volume minus P of volume. So this is a very important relation. So this equation is basically known as the energy equation. Okay. This shows how the internal energy changes with volume. Okay. In that perspective, this this relation is very important. This is a very general relation. You can use it for any kind of systems. Okay. To use it, basically one thing that we need to know is the equation of state for that particular type of fluid or gas, whatever it is. Like let's take for the case of a Van der Waals gas. So for Van der Waals gas, we know the equation of state looks like this. So Van der Waals T plus A by B square equal to P minus B equal to RT, right? So you can write it as P equal to RT by B minus B minus A by B square. Okay. Now to compute it, first thing that we need to calculate is del P by del T, right? So del P by del T would be at constant volume, obviously it would be R B minus B. Okay, so you calculate del P by del T. So now just substitute these things here. So, okay. So del U del B would be RT B minus B plus P. Now you can also write it as using this. So RT V minus B minus P is basically nothing but from this relation you can write it as del U del B equal to A by V square, right? Okay. So this is the change in entropy. Now del U del V you would already know, and del U del T also is nothing but the Cv. at constant value is nothing but the Cv. So del U del V you know, del U del T you know. This is at constant temperature. So from it you can write du as del U del V at constant temperature dV plus del U del T at constant volume dt, right? So you know del U del V is basically A by V square dV minus, sorry, plus del U del T is nothing but Cv. So Cv into dt. If you do the integration, so del change in entropy, change in internal energy delta U would be minus A by V. There will be some integration limit V1 to V2 plus Cv delta T, some temperature T1 to T2. This is for the case of an real gas, van der Waals gas. Okay. Similar way, for any kind of gas, different types of gas equation, whatever it will be mentioned, you can calculate its corresponding change in internal energy just by using their equation of state. Okay. Next thing is like so we will now like formally we know that the Cp and Cv we can write in terms of as a function of their entropy, right? So we know that Cp, the heat capacity at constant pressure, you can write like T delta S, T delta T at constant pressure. We know Cp is basically dq by dt at constant pressure. So dq you can write as TdS. So from there you can take this form of expression for Cp. Now, so this form is not a very convenient form, okay, because in order to calculate in this format, okay, in this format, in order to calculate the Cp, you need the information of the change in entropy, which is not a very easy thing to calculate in a real thermodynamic system. Okay. So it's better to write in terms of the variable that we are already as a like familiar with. Okay. So for in order to write the Cp in terms of familiar variable, what we can do, we can take the use of Maxwell's relations here. So Cp you can write as so we'll basically use this thing. So del S, you know, if S, P, T are S, P, T are three variables, then you can write it as del S del P at constant T into del S del P del T at constant S into del T del S at constant P equal to -1. Okay. If these three are basically dependent variable with each other, so in that case you can write these three variable. You can use this relation among these three variables here. So you can write del S del T as minus T into del P del T at constant S into del S del P at constant T using this relation. Okay. So still there are terms involved, entropy is there. So del S del P at constant T. Now we will use the Maxwell relation. So using Maxwell relation, you can write del S del P at constant T equal to minus del V del T at constant P. Right? So we'll substitute it here also. So after doing that, we get del P del T at constant S into del P. So minus minus will become plus del V del T at constant P. Okay, so this is a very useful relation to remember. Okay. That is the Cp, that is the specific at constant pressure in terms of pressure, temperature, and volume. Okay. Similarly, for the case of Cv also, you can write it in like so Cv expression is in general written like this: Cv equal to T del S del T at constant V. So this relation also you can write it like this: minus T del V del T at constant entropy S into del S del V at constant T. Okay. See, these two are very important relations to remember. Or next step we also have del S del V also you can write in using the Maxwell relation. So minus del S del V, del S del V. Yeah, del S del V can write it as del P del T, right? So this thing del S del V you can write it as um, del P del T. That constant volume is, yeah, constant volume. Okay. Now also similarly, so these are the CP and CV. Next relation you can write the first is the difference between CP and CV. Okay, so CP minus CV. That relation is previously defined as this T into this relation you can write in terms. So for ideal gas we know CP minus CV equal to R. Okay. So this is for the case of an ideal gas. Okay. For one not in for ideal gas. Okay. Now there is also a general form of the CP minus CV. Okay, general for any type of gas you can basically use this general formula of CP minus CV. So that formula is coming from basically by taking S as a function of two independent variables T and V. From there, if you write uh, the ds equal to del S del T at constant V dt plus del S del V at constant T dV, and after doing some algebraic manipulations, you can write this thing as T del S del T at constant T minus T del S del T at constant V equal to T into del P del T at constant V into del V del T at constant T. Okay. So this is a useful relation. Now from here, so T ds dt at constant you can write it as Cp minus T ds dt at constant you can write it as Cv equal to so T del P del T at constant V del P del T at constant. Okay. Now you can also write it other ways also, depending upon the nature of the problem. You can substitute the expression of volume expansion with alpha 1 by V del V del T at constant P. The compressibility, that is Et equal to minus V del P del V, or expansion, isothermal expansion, At equal to 1 by V del V del P at constant T. So you can use all these definitions also here into the expression of Cp minus Cv. By doing that, you can write two more expression of Cp minus Cv, that is Cp minus Cv equal to Tv Et alpha square, and Cp minus Cv equal to Tv alpha square Et. These are also two expressions. Now, uh, now the next thing that we'll discuss is how the CV CP is change with volume. Change with CV change in volume means basically, let's suppose you have a gas in a small container. Okay, let's suppose small container U of B small. Then you same gas, same amount of gas, if you take it to a larger volume VB. Okay. So in that case, what is the change in CV specifically, and CP? CP in the case would be pressure. So how does this thing changes the CV, the measurement of CV? So that to basically measure that, we will use this form. CV we know, so we will basically write the equation for that. So CV we know, T delta is delta T at constant V. So we are changing the volume. So delta CV at delta V at constant temperature will be T into delta del V into del S del T at constant volume. This thing will be at constant temperature. Okay. So now this way you can write it as delta CV delta V at constant temperature will be T into delta del T into delta S delta V at constant temperature. So delta S delta V at constant temperature, and write it like this: delta S delta V at constant temperature, and write it as del P del T at constant volume using Maxwell relation. So del CV by del V at constant temperature T into del T or P by delta T at constant volume. What you can write is T into del square T del T square at constant volume. Similarly, so this is del CV del V at constant temperature. Similarly, we can also calculate what is the change of Cp, specific it at constant pressure, specific it at with respect to the pressure. So del Cp del P. Similar way, T into del P of del S del T at constant pressure in constant temperature. Similar way, if you do some algebraic step, we will get del Cp del P equal to minus T del square V del T square at constant pressure. This is also very important relationship. Okay, so these two basically relationship gives you how the specific heat is changing with respect to the volume and with respect to the pressure. So now we'll discuss some of the thermodynamic functions. Okay, so right now we have only discussed about the internal energy as a thermodynamic function. There are other several thermodynamic functions are there. Okay, so the first thermodynamic function is known as the enthalpy. Okay, we know enthalpy is basically H equal to U plus PV. Okay, this is the standard algebraic definition of enthalpy. Okay, we write it as enthalpy. Mathematical description of enthalpy. So it's basically addition of internal energy plus pressure into volume. Okay. Now yeah. Now you can write it as dH change in enthalpy would be du plus PdV plus VdP. Now you already know dq equal to du plus PdV, that is basically dW. So the substitute this thing here, so dH will become dq plus VdP. Okay. Now there is a significance of this enthalpy. First significance is you can use this thermodynamic function in order to directly calculate the Cp. Okay, the specific heat at constant pressure. Now previously you know Cv is basically del U by del T at constant volume, that we have derived much earlier, right? Similar way, so here Cv is directly related with the internal energy as a thermodynamic function. Now for the case of Cp, is you can write it as dq dt at constant pressure. This is the fundamental definition of Cp. Now from here, using this relation here, dq you can write it as dH minus vdp, and P simply is constant, so vdp will become 0. So Cp you can write it as dH by dt at constant pressure. Okay. So this is, so you need the internal energy in order to calculate the Cv, specific heat at constant volume, and you need the enthalpy to calculate the Cp. Okay. So this is one of the importance of the enthalpy. The other thing is that for different types of processes, we can relate this change in internal energy with different things. Like for the case of an isobaric process, try to remember this. It's a very important relation, how the enthalpy related with other change in enthalpy related with the change in other thermodynamic functions. Okay. So for isobaric process, change in entropy delta H is dp 0, so delta H will be delta Q. Similarly, you can write this other thermodynamic quantities like temperature and volume also in terms of enthalpy. So in how to do that? So for the case of enthalpy, I'll show. So dH is dq plus vdp, right? So dH dq you can write as TdS plus vdp, right? So that means enthalpy is a function of two independent coordinates, and one is S and one is P, right? From its expression, we can easily see. So dH would be del H del S into ds plus del H del P into dP. So by comparing these two, you can write T as del H del S. This is at constant pressure, this is at constant enthalpy. So del H del S at constant pressure, and P would be del H del P at constant enthalpy. These are also very useful formulas. So you can, by knowing the enthalpy also, just taking some derivative for any general system, you can calculate its temperature and the volume also. Okay. So this is many different use case of the enthalpy we have seen right now. Next is the, what is this? This is the Helmholtz free energy. Okay. Next quantity is known as Helmholtz free energy. For the case of Helmholtz free energy, the thermodynamic function looks like this. So it's denoted by F. F equal to U minus Ts. U is the internal energy. Now from here, you can write dF equal to du minus Tds minus sdt. Similar way, from the definition of first octane, we can write it as Pdb minus sdt. Okay. So here also you can take for an isothermal process, for dt is 0, the change in free energy delta F would be directly equal to minus of the work done, delta W. So in case of isobaric process, the heat change is equal to directly equal to delta H. Yeah, and for an isothermal process, the negative of the work done is equal to the change in the Helmholtz free energy. Okay. Similar way, in that you can write the other thermodynamic coordinates like pressure and entropy in terms of the free energy. So pressure is minus del F del P at constant temperature. Entropy is minus del F del T at constant volume. Okay. Same way, the derivation is same as the way we have done for the case of enthalpy. Okay. Third is the Gibbs free energy. So the thermodynamics definition of Gibbs free energy looks like this: G equal to U plus EV minus Ts. Okay. So this is the uh, definition of Gibbs free energy: G, U plus PV minus Ts. Also, you can write U plus PV as the enthalpy H, right? So it's equal to, right, you can, U plus PV is H minus Ts. Also, you can write U minus Ts as F. So you can write it as F plus PV also. So either way, whatever according to your convenience, you can write in terms of enthalpy or in terms of free energy, almost free energy. Okay. So now, so similar here also you can write, you can express the change in Gibbs free energy as in terms of change in the other thermodynamic coordinates, like equal to VdP minus SdT. Okay. So now, okay. Also, you can write the other, like, so you can see G is basically function of pressure and temperature, independent variable, that is temperature. So, so you can write the other thermodynamic variables like volume in terms of Gibbs free energy. So V will be del G del P at constant temperature, and entropy would be minus del G del T at constant pressure. This is also a very important relation to remember. Now here, from this expression, you can see for isobaric, that means dP will be equal to 0, and isothermal, that is dt equal to 0. The del dg delta g will be always equal to 0. Okay. This is a very also important thing to remember. So isobaric and isothermal process means basically any kind of phase transition that is occurring. Okay. So that is a kind of a process where pressure remains constant and temperature also remains constant. Okay. So also for this kind of processes, the change in the Gibbs free energy would be equal to 0. Okay. Next, we will discuss about the Gibbs-Helmholtz relations. Okay. So, what is the Gibbs-Helmholtz relation? It's basically is a relation between two thermodynamic functions, H, enthalpy, and interenergy U, as a function of F and G. Okay. Sorry, G and F. Okay. So H will write as a function of G, and there will be other coordinates also will be there, and similarly U will be function of F and other coordinates. Okay. So how to do that? So for that we first write the U. So U we know equal to, so F we know, F is basically equal to U minus Ts, right? So U is basically F plus Ts. Now S we know, S is so S we have to write in terms of F actually. So from Helmholtz free energy we know S is equal to minus F del F minus del F del T at constant volume. So just substitute this thing here, minus del F del T at constant volume. So we substitute this thing here, so it will give you U equal to F minus T del F del T at constant volume. Okay. So you can write this E in terms of, so you can basically, if you measure, this is basically gives a relation, you can say, between free energy and internal energy, right? Next is the next we write enthalpy. So similar way, enthalpy also you can write in terms of gives free energy actually. Okay, so uh, H we know is equal to G plus Ts. So after doing some algebra, you'll get H equal to G minus T del G del T at constant pressure. Okay. This is also a very important relation. Okay. So next we'll discuss that for different processes, how different thermodynamic functions changes. Okay. So for that, so in order to check that first, what you have to do, you have to consider the change in entropy. Okay. So okay. So we know that delta S universe, sorry, delta S universe is basically because delta S, that is change in entropy into the system plus delta S, that is the change in entropy in the surroundings. Yeah, okay. And for any natural processes, we know delta S universe is always greater than equal to 0. So by doing that, by increasing this change, by increasing the change in universe of the whole, change in entropy of the whole universe, the system tries to achieve equilibrium. Okay. So main reason of this increase in entropy is basically to uh, attain the equilibrium distribution for the system. Okay. Now this delta S U, so we know this delta S surrounding is basically nothing but minus dq by t, right? Dq because there is heat that is getting output into the surrounding. So now this thing can write it as minus du plus pdv at a fixed temperature. Let's take T0. Okay. Now if you substitute this thing here, this is for surroundings, and if you've done some algebraic manipulation, you'll get this condition. Okay. For equilibrium, the condition becomes du plus T0 dV minus T0 ds if this more equal to 0. This is the general case of the equilibrium. Okay. This quantity also you can write it as a variable a. Okay, so we can write a as d plus p0 d plus sorry minus p0 s. Okay. So dA we can write it like this. So dA is basically nothing but this thing, right? So dA is always less than equal to 0. This is the condition for it. So now we will check for different cases, okay? For different special cases, by observing those cases, we'll see what are the thermodynamic functions that needs to be changed in order to make that particular system to be in thermodynamic equilibrium. Okay. So we'll consider different specific cases. Okay. So first case is case one is diabatic and isochore. Okay. For adiabatic and isochore, we know ds equal to 0, dv also equal to 0. So dA, so you know dA would be always will be less than equal to 0. Now in ds, so ds and dv is already equal to 0. So that means the only term that is remaining is du. So du would be smaller than 0. So that means we have to, for case an adiabatic isochoric, we have to minimize the u to achieve equilibrium. Similarly, for case 2, for fixed entropy and pressure. Okay, fixed entropy and pressure. So fixed entropy and pressure means delta S is equal to 0 and delta P is also equal to 0. Now in our in our expression, so if we make delta S equal to 0 and P delta P is equal to 0, so dA less than 0 will become du plus P0 PdV less than equal to 0. So du plus PdV is nothing but dH should be less than equal to 0. So minimize the H. For the case of isentropic and isobaric process, fixed entropy and pressure. Okay. Case 3, fixed volume and pressure. For fixed volume and temperature, so dt is equal to 0 and dv is equal to 0. So now if we put this thing also in the expression of dA, so dt and dv, so it will become du minus tds less than equal to 0. So that means df should be less than equal to 0. And case 4 is isothermal, isobar, and isobar. So isothermal and isobar means dt equal to 0 and dp also is equal to 0. That means dt and dp. So this expression will become du minus t0 ds minus plus t0 dp should be less than 0. And this quantity is nothing but the change in this dg, so dg will be less than 0. So this is the condition for equilibrium. So for different cases, you can see different thermodynamic quantity, thermodynamic function needs to be minimized in order to achieve the equilibrium of the system. I will take the last thing is for thermodynamics of chemical reactions. So for chemical reaction, you will see what is the condition. Our chemical reaction looks like this: A plus B, preview product C plus KO. Now, if it's a process that is at constant pressure and temperature, so if it's fixed pressure and fixed temperature, so in that case, we know in order to happen this process simultaneously, delta G of that during the process, delta G during the process should be less than 0. Okay. In order to spontaneously happen, spontaneously occurrence of this process. Okay. Occur spontaneously. Now, if you see the delta G during the process greater than 0, so that means for this process you need to pump energy. Okay. So, so it's not like just only the initial and product terms that are required to find out whether this process is spontaneous or not. You have to also check the in between steps. Okay, so in a free energy diagram, Gibbs free energy diagram, at constant pressure and temperature, this things looks like this. If you plot the Gibbs free energy G, and with respect to any kind of reaction coordinate, okay. So for reactant, well, maybe it's A plus B has a higher value compared to the product. Okay, C plus D. But so by seeing that, it may looks like the process can spontaneously occur, but in between maybe there is a activation energy unit. So in between it has a curve like this. Okay. So if it's a curve like this, then it comes back to the product state. Okay. So although the delta G, if you only consider the first initial and end product, then the delta G is quite negative. But in order to climb this extra activation energy level, so you need some external force like catalysis or whatever in order to make this reaction happen. Now we'll look into some problems. The problem one is use the first law of at constant temperature in terms of Cp and Cv and beta P. Beta P is nothing but that volume expansibility. Okay. Coefficient of volume expansibility. Okay. So the options are Cp plus Cv by P into beta P minus P. Option B is Cp plus Cv P into beta P plus P. C is Cp minus Cv P into beta P minus P. And option D is Cp minus Cv P into beta P plus P of P. So these are the four options. So so you have to express du del v in terms of distance. Okay, so in order to do that, you have to use the first term parameters. Okay, so first term parameter is du equal to dw plus dq. So dw you can write it as pdv plus, sorry, uh, yeah, equal to du plus dw. So du you can write it as dq minus pdv. Okay. So now, PDV, yes. So now dq. So another way you can also write u as u will be the function of volume and temperature, right? So du would be the total derivative. Du would be del u del t at constant volume dt plus del u del v at constant temperature dv. Okay. So the substitute this thing here. So after doing that, you will get dq as del u del t at constant volume dt plus del u del v at constant t plus p into dv. Okay. Now from here, so uh, now we can write dq dt at constant pressure is equal to du dt at constant volume plus del u del v at constant temperature plus p into del v del t at constant pressure. Now dq dt at constant pressure you can write it as Cp. So Cp would be, and also this del u del t at constant volume you can write it as Cv plus this thing will become unchanged, del u del v at constant t plus p. And next is that beta p is nothing but 1 by v into del v del t, right, at constant pressure. So del v del t you can write it as v into beta. Okay, so that means you can rearrange the term, so it will become del u del v at constant temperature will become Cp minus Cv divided by p into beta minus p. Okay. the correct answer would be this one. Cp minus Cv will be option C. Okay. Okay, so the thing is like we have to first use the first law of thermodynamics, and from there uh, you have to write also the du in terms of total derivative. Now the total derivative thing you have to substitute in the first law of thermodynamics. Then after that you use you use the expression of Cp and Cv whatever it is necessary. Like here you can basically rewrite dq dt as Cp and du dt as Cv. And next also you have to write in terms of beta. So beta, you can substitute this beta in here actually. So dv dt, you know, beta is nothing but beta equal to 1 by v into dv dt at constant pressure. So you can see here you can substitute this beta. So after doing that, you will get this expression. So in this expression, just you have to write du del v in terms of other variables. So this is this. After doing that, this will be the correct answer. Okay. The next problem is problem 2. If ideal gas of 1 mole under pressure E has density 0 and its molar specific heat at constant volume, that is Cv basically, Cv, and Cp by Cv is equal to gamma, then the entropy of the gas is expressed as, so options are option A, Cv ln P by rho, rho is the density of the gas, to the power gamma plus 1 plus some constant T, B is Cv ln P into rho 1 minus gamma plus A, this is Cv ln P rho gamma minus 1 plus some constant P, and D is Cv ln P plus rho gamma plus some constant rho. These are the 4 options here. So which are the correct? So the question is you have to calculate the entropy of the gas. Which are the correct form you can basically write, you can express it. So first what we have to do is to write the expression of entropy in terms of as a function of 2 independent variables. So here we take entropy as a function of temperature and volume. Okay. Change in entropy ds, so total change will be del S del T of constant V dt plus del S del V at constant T dV. Now this part you can write as Cv by T, since Cv is nothing but dq by T, that is Tds by dt. So from there you can write del S del T as Cv by T into dt plus del S del V. From Maxwell relation you can write del S del V as del P del T at constant V dV from Maxwell's relation. Okay. Now here it's mentioned it's for a case of an ideal gas. Okay, so for a case of an ideal gas, P we know RT by V. So dP by dt is at constant volume would be uh, R by V, right? So the substitute this thing here, so it will become CV by T into dt plus R by V into dV ds. So now if you do the integration, it will become delta S would be integration CVT into dt plus R by V dV integration. So after doing that, it will become CV into ln T plus R into ln V plus some constant K. Okay. Now this thing, so yeah. Now we know T PV equal to in RT, right, for 1 mole n equal to 1. So ln of PV you can write it as ln of RT equal to ln of T plus some constant. Okay, K prime. Okay, K prime, let's suppose is ln of R, that is the R is constant, so K prime is also constant. So CV into ln of uh, PV. Okay. So that constant K prime will become this side, so it will become R into ln V plus K minus K prime. Okay. Now this thing can write it like this: CV into uh, yeah. So now we can take CV and ln as common, so it will become P V to the P into 1 plus R to the power CV. Okay. This is nothing but we just rewrite this thing as uh, if you do you write this R as, so R we can write is like this. So CV into ln of uh, can take CV as common into ln of P into R by CV. Okay. So if you rewrite this R ln V like this, then from there you can basically rewrite this expression like this, and this whole constant will become a single constant C itself, or you can say some K double Q. Now from here you can write CV equal to ln of E V into gamma, because you know uh, for case of any kind of ideal gas, gamma is equal to 1 plus R by CV. Okay. Plus K double Q. So this means the entropy expression would be, correct expression would be, okay. So in terms of rho, actually have to calculate. Okay, so volume is against so volume is mass by rho. Rho is mass by volume, so volume is mass by rho. So S would be, so rho would be denominator, right? So it would be become CV into ln P into rho to the power gamma plus some constant. Okay. After substituting this question. So the correct answer would be this one, the option D. The thing is that this is a very between the steps you have to algebraically you have to be very precise. Okay, like you have to always keep in mind what things you have to prove. Okay, so according to that you have to basically make suitable algebraic calculation and all. Okay, so by doing that only you can get the desired answer. Okay. Now, the problem number 3. Estimate change in entropy for a gas following the equation of state P plus B into V equal to R2 and undergoes isothermal expansion from volume V0 to V0. The options are option A, R ln 2, option B, U R ln 3, option C, R plus B V0 ln 2, and option D, 3R plus B V0 ln 2. Okay. These are the 4 options that are given. So change in entropy to calculate from basically from its equation of state. So for that we will basically use one of the Maxwell relations actually. So from Maxwell's equations we know that del S del V at constant temperature is equal to del P del T at constant volume. Okay. And for this particular gas equation, del P del T at constant volume nothing but R by V. So substitute this thing here. So del S del V at constant temperature will become R by V. So it will become D is equal to R dV by V. If you integrate it, it will become delta S R into volume. So the volume is changing from V0 to 2V0. So it will become dV by V. So if you integrate it, it will become R ln of 2V0 by V0. So it will delta S will be R of ln 2. This will be the correct answer. So it's easy, just have to use one of the first Maxwell relation. From there, del P del T is, you already know, for this particular equation of state. So del P del T is nothing but R by V. It would be the derivative of this equation of state. substitute that thing here. So from after doing that, just do the integration in order to get the change in entropy. Okay. Next is question 4. Expression del P del P constantly del T P at constant is minus del T at constant P is equivalent to option A del S del V at constant in option B minus del V del T at constant S option C del V del T at constant in option D del S del V at constant minus del S del V at constant. So answer is so first write the thing, so that is del P del V at constant T del P del T del P at constant S and del S del T at constant P. So this del, so from Maxwell relation you can write del T del P as del V del S. So del P del V at constant, you can write del T del P as del V del S at constant P, and you can write the del S del T as it is. So now dv cancels, it will become del P del S at constant T. So yeah, and it will become del V will remain itself. So ds will cancel, so it will become del V del T at constant P. Now so del V del T you can also use the Maxwell relation. Del V del T using the Maxwell relation, you can write it like this: minus del S del P at constant T. So dp will cancel, so it will become minus del S del V at constant T. So the correct answer is option D. Now the question number 5. For dynamic system, the expression T delta S delta T at constant V minus T delta S delta T at constant V is always equal to option A 0, option B Cp by Cv, option C isothermal elasticity ES, and option D T into del P del T at constant B and del V del T at constant P. Okay, so these are the 4 options. So to do that, okay, first write the entropy as a function of temperature and volume. just as it is, we are writing throughout all the problem. So ds is delta s delta t at volume dt plus delta s delta v at constant t dv. Now if we put the derivative ds dt at equal to delta s delta t at constant volume plus delta S delta V at constant temperature, del V del T at constant pressure. Okay. This is also a constant pressure. Okay. So now, if you multiply T both the sides, so T delta S delta T at constant pressure minus T delta S delta T at constant volume will be equal to T into, so delta S delta V from the Maxwell relation you can write it as del P del T at constant volume into del V del T at constant pressure. So this would be the relation. So the correct answer will be the option D. Okay. Last problem number 7. If the equation of state is given by V equal to RT by P minus V by T square, where D is a constant, which of the following relation is true? Which of the following relation is true? First relation is option A is del Cp by del P at constant T is T inverse. Option B is del Cp del P at constant T is will be T minus 2. Option C is del Cp del P at constant T T to the power minus 4. Option D is del Cp del P at constant T to be proportional to T to the power minus 3. These are the 4 options given. So which are the correct ones? So we already discussed, right? So the how the specific heat at constant pressure, like Cp, how that Cp like with, what is the derivative of Cp with respect to P? That expression we have already covered into our discussion. So that is given by del Cp by del P at constant temperature is basically given by minus T del square V del T square at constant pressure, right? So that means since the equation of state is given, so we have to calculate this quantity. Okay, so that will do. So the equation of state is this basically. So V would be RT by P minus V by T square. So del V del T would be RT by P minus 2B by T cube, right? Plus 2B by T cube, sorry. So del square V del T square at constant P, so over constant P will be minus 6P T to the power 4. So we just substitute this thing here. That will give us del Cp at del constant del P at constant T will be minus 6B into T to the power minus 3. Okay. Now, so this was problem 7. Now problem 8. This is problem 6. Sorry, this is problem 6. This is problem 7. Calculate the difference Cp minus Cv for mercury at 0 degrees centigrade and at pressure equal to 1 atm for mercury. Compressibility K is given equal to 38.7 into 10 to the minus 12 meter square Newton inverse. Expansivity that is beta basically is given by 18 into 10 to the power minus 6 Kelvin inverse, and density of mercury, density is rho, that is 13.6 gram per cc, and molar mass M is given by 100.6 kg per kilomole. So in that case, you have to calculate Cp minus Cv, right? So the options are option A, 50.3 kilojoule per kilomole per Kelvin. Option B is 33.7 cell unit. Option C is 42.4 cell unit. Option D is 56.8 cell unit. Now for that, we already know the formula of Cp minus Cv, right? We have derived, we have shown that Cp minus Cv is beta square Tb by K. Now here it's so beta is, we already know beta value is 18.10 to the minus 6. K we already know is 38.7 into 10 to the minus 12. T we know T 0 degrees, so 273 Kelvin. And the V, so V is basically m by rho, right? Mass by density. So mass and density both we know. So just substitute the thing. So 18 into 10 to the power 6 minus 6 whole square into 273 into 200.6 into 10 to the power 3 divided by 38.7 into 10 to the minus 12 into 14.6 into 10 to the power 3. Now if you calculate this, it will give you around 33.7 kilojoule per kilomole per Kelvin. Cp minus Cv. This would be the answer. Okay. So that's it. So this is our last problem. So we have come to the end of the class. So if you have any question regarding today's class, you can ask, or whatever you guys post that class. So then I'll post the class.